And then finally, we want to look at the quality factor. Now, the quality factor tells you about the damping of your cavity. It tells you it's the number of oscillations that happen after you turn the power off before your cavity is completely died out. So how many oscillations before there's no more energy left? And for our cavity, it's about 8,000. It's a normal conducting cavity. If you look at the superconducting cavities that are being used further down the line, really cool thing to know is they've got a Q of about 10 to the 10. And if you go back to the days of Galileo, who was one of the first people to work on research with pendulums and oscillations of Q, if his pendulum back then had a Q factor, like the ones we have in our cavities today, he pushed that off back then when he was working on it. It would actually still be oscillating now at about half the frequency, or half the amplitude. It's pretty impressive. So another thing we want to make sure is that our fields are what we expect them to be. So now we've built our cavity, we've assembled it. We've got to make sure that we're getting the fields that we expected from our simulations. This is actually kind of tricky to do because when you probe an electric or magnetic field, you're going to affect it. We can actually use this to our advantage. So Slater's perturbation theory says that if you have a small conducting volume, like a bead, or BTBs, or on the picture on the left, if you have that, and you run it along through your cavity, the resonant frequency of the cavity will change depending on the fields that are around it. So what we do is we run these beads through our cavity, and we can actually work backwards to get the electric and magnetic fields. But you'll see we use two beads. We use a dielectric bead and a conducting bead, because we need the dielectric bead to give us only the electric field, and then the conducting bead will give us the electric and magnetic field according to that equation there, and we can subtract what we obtain with the dielectric bead to get our magnetic fields. So you can see we have some fields determined experimentally that look very similar to our simulated fields. So with that in mind, we were able to install the deflecting cavity in the injection line, and we've actually started doing some tests with it. And that's just been happening in the last month. It's pretty exciting. We can see on the left here, this is actually a picture of the beam, and you can see with the deflecting cavity off, we have a nice round beam. But when we turn it on, all of a sudden we have a whole bunch of spread in the y direction, which is exactly what we were looking for. You can also see it in this graph here, which shows you the phase dependence as well. So these peaks are the position in the y direction of our beam. You can see if the deflector's on, depending on the phase offset of the deflector, we will see the y position of our beam shift, and also the spread in the y position. So we have really good data, but now how do we go backwards and take this data and turn it into our time? From this data, we want to get the spread and time domain beforehand. For that, we need to do some more simulations. And instead of just doing particle simulations, we need beam dynamics, because when you have several particles, they're going to interact, which is what we have in a beam. So for this, we're using a program called General Particle Tracer. And this here shows you very clearly, these are just particles, but shows you very clearly what's happening in the deflecting cavity. So on the left, at the start of our graph, that's just the start of the deflecting cavity, and it goes to the very end of our graph. And you can see, depending on the base of the deflector cavity, you're going to get different trajectories in the deflecting cavity based on the time of arrival. Now, particles are good. We double checked that this is what we got back when we did the simulations with CST and MATLAB. Let's look at beam. So now that we have a beam, once again, just to orient you, this is in our deflecting cavity. So end of the deflecting cavity happens at z is equal to 0.2. And we're looking at the y plane of our beam. This is a cross-section in the y has also some spread in the Y. So that's what we're working on right now. And to conclude, what did we do? Well, we designed a cavity that deflects electrons based on their arrival time. And we simulated this using CST Microwave Studios. We did some particle dynamics in MATLAB, CST. And then we built this cavity. We assembled it and we tested it. We used the bead pulling technique to get our on-axis field to make sure they were what we expected. And now we're actually running the cavity with beam and doing beam loaded testing. So what's left to do now is to actually take our results, take our beam dynamic simulations that we're working on, and make that into a program of some kind that will allow all users of the beam to simply, with a click of a button, find out what the bunch length is. And that should help for not only for us in terms of keeping a good quality beam, but also for people that need to know this information for their experiments. So with that, I would really like to thank Triumph, and in particular the SRF group for their expertise and guidance. In fact, we have a low-level RF engineer from Triumph here today, and he was very instrumental in getting the low-level RF done for this deflecting cavity. So I'd like to thank them, and I'd also like to thank you for coming.
Thank you, Alysson, for that talk. Do we have any questions for Alysson? Yes.
You mentioned that you're going to let the user, when they get the shot, to be able to measure the spread of their beam in kind of a per run basis. You actually also expect to have regular beam monitoring, regular time intervals throughout the entire use of the EMF?
Yeah, well, I mean, I think it can't be run all the time because it's destructive testing. So you're not going to get any beam while we're testing something like that. There are a lot of devices that are installed currently and that they're working on developing right now that will be non-destructive but can be running while you're running beam too.
And how long does this sort of test take? How many,
to get the data itself
Yeah.
is instant. I mean, you just need to turn beam on, and to get one of those profiles takes a minute and a half, but we can also get the screenshot like instantly.
Can you go back to slide number 8? Yeah, so the actual data. Do you know why it's a little bit smaller?
Yeah, actually. So the tails, you'll notice, are narrower. And the reason for this, as I mentioned before, we want to drive this cavity at the resonant frequency. And if we go back even further, let's go back to here. You can see that this cavity has these nose cones sticking out. And if you notice the nose cones, that's where the fields are the strongest. These nose cones also affect the resonant frequency. And when I said we wanted to drive it on that frequency, we had to tune our cavity once it was built. And this is an unexpected thing that you have to do. You build it, and then you use network analyzer to find out the resonant frequency. And then you have to trim these nose cones to get to the proper frequency. So get to 1.2 gigahertz. But now the nose cones have changed compared to what we saw in our simulation. So what that actually does is it will change your field a little bit, and it will change the point at which they really come into effect. And that's what's giving us these narrower electric and magnetic fields, because we've done some trimming of those cones. Thank you.